Hello everyone. In this video we're going to take a look at parametric equations. Now you may be in trig class with me or pre-calculus. You may be in Math 5B or you may be in 5C where you're looking back at a little review. In the Math 5B book, this is section 10.1, but whichever course you're in, it is in your book somewhere. All right, so here's the idea. So far we've learned how to express any equation in two variables. Let's suppose those variables are x and y, but we know they don't have to be x and y. If we look at any equation in two variables, we know we get a graph in two dimensions. So if we're working with x and y, then we have the x-axis and the y-axis, and this would represent the relationship between x and y. Sometimes we can take that equation and solve explicitly for y, in which case we say y is a function of x. And we know that to determine whether or not we have a function of x, we use the vertical line test. For any given x, there can only be at most one y, then we do have a function of x. Sometimes when we have that equation in two variables, we can solve explicitly for x in terms of y. So if we can solve for x in terms of y, then we'd say this is a function of y. And so to determine if we have a function of y, it's not the vertical line test. Instead, what we're doing is we're saying, here's my input. We have to get used to looking at things differently. Here's my input y. For every given input y, there is only one output x. Then indeed we do have a function. And as you know, there are some curves that can be written either as a function of x or as a function of y, or both. Okay, but we also have some equations in two variables that aren't functions at all. Here is one, for instance. If we try to solve for y or we try to solve for x, we don't get a function. In fact, if we tried to solve this for y, we would get y equals plus or minus the square root of 1 minus x squared. And that plus or minus is an indication that we don't have a function, because it is telling us that for a given input x, there are two different outputs, and that is not a function. And we can see that with the vertical line test. For a given x here, there is more than one corresponding value of y. So that is not a function, but it is still a relation. Okay, this is kind of off topic for just a minute, but when you want to work with a circle, which we do quite often, if you do want to work with something that is a function, what you would have to do with this is break it into two separate pieces. The top piece here would be y equals the positive square root of 1 minus x squared, and the bottom piece here is y equals negative the square root of 1 minus x squared. So if you were doing some sort of work that required functional form, then you'd have to know if you're dealing with the top part or the bottom part. The thing as a whole is not a function, but we sometimes say this is locally a function. This piece is a function, this piece is a function, separately. Okay? All right, so what we're going to do new today is we're going to consider another way to write equations for curves in R2. And what we're going to be looking at is called using parametric equations. Parametric equations. And this gives us the opportunity to do two things. The first thing is to show dependence on a third variable. And the second is to take something like this that's not a function, a single equation that's not a function, and write it in terms of individual equations that are functions. That doesn't sound very clear, I know. We'll get to that. So write an equation in terms of two functions. Again, that'll become more clear later. So for the first idea that we're going to look at, showing dependence on a third variable. I actually found what I thought it was an interesting introduction to parametric equations. It is on my Math 5B page, and it's under the link Quick Intuition About Parametric Equations. But suppose you saw this relationship. Seems kind of weird in a math class. What does that have to do with anything? Well, when we have an equation in two variables, we're often looking at the relationship between those two. How does this depend on this? How does this output depend on this input? So in this case, if you looked at this equation for two entities, it seems that the amount of ice cream that is sold at a given store is related to the amount of sunscreen that's sold squared. So if 3 bottles of sunscreen are sold, then 9 ice creams will be sold that day. But it gives you the impression that, oh, okay, so ice cream is a result of sunscreen. Like buying the sunscreen is what makes me want to buy the ice cream. And that's not likely the cause and effect. There's likely some deeper connection that's not stated here. You can think about what that would be. Likely, it's the fact that they're both dependent on temperature. It might be something like, when the temperature goes up, so here's 80, 90, 100, the amount of ice cream sold goes a lot higher. And separately, when the temperature goes up, people are needing to buy more sunscreen. So the fact that ice cream goes up with sunscreen is true, but it's not necessarily causal. They are both related to some other variable. And so we call that variable a parameter. So there are a lot of times when we have an equation with two variables where there's some other underlying connection that's not apparent. That's the idea of parametric equations. And often, though not always, but often that parameter is time. And we'll look at that in the next example. Okay, so let's take a look at this example. Suppose you were asked to sketch this pair of parametric equations. Now we're brand new at this, so I would have no idea how to start. And when we have no idea how to start with a graph, we often go to plotting points. So that's what we're going to do first here, just to explore. But in reality, once we learn some techniques here, this should be your last resort. Okay, so by the time we get to a test, I really don't want to see you plotting some of these by doing what I'm about to do. All right, this is our last resort. So what do I mean by plotting points? I mean that for a given value of t, we put in some value of t, we'll get out a corresponding x and y. So for instance, if t equals, let me just randomly put in some numbers like -2 or -1 or 0 or 1 or 2. If I put -2 into here for t, I'm going to get 1 minus a minus 2, 1 plus 2, I'm going to get 3 for x. And if I put in a -2 here, I'm going to get 4. Okay, similarly for all the other ones. All right, so what do we do with those points? Let me jump down here. Notice this is an XY plane. So I would be drawing the XY coordinates here. So I have the point 3, 4. So 3, 4, 1, 2, 3. Looks like my 3, 4 is off my graph a little bit. And then I would have the point 2, 1. And 1, 0. So 2, 1 would be here. 1, 0 would be here. I have 0, 1, and -1, 4. So 0, 1, and -1, 4 would be up here. Now notice this graph is just in terms of x and y. There's no t on here. If we want to keep track of what's going on with t, what we can do, what we sometimes do, is maybe right next to it write that this point here, 3, 4, that corresponded to t equals -2. It's just extra information that we may or may not want to carry along. This one corresponded to t equals 0, t equals 1, and t equals 2. All right. Actually, my picture looks a little off here because 3 is here. So 3, 4 would be here. Okay. All right, so these are all points that satisfy this pair of parametric equations. These would be points on the graph. Now you might think, oh, it kind of looks a little like a parabola. I'll just connect the dots. Well, that's true, it does, but we're brand new at these things, so we shouldn't really assume that that's what's going to happen. Maybe it goes way over here and so on. Okay, but that would be how we would use the point plotting technique. We would plot a lot more points until we're really convinced what that graph would be. Okay, so that's method number 1, last resort. Another method, and this is a pretty interesting approach that is actually going to become very useful as we go on, is to look at the graphs of x of t and y of t separately. And so what I mean by that is this equation here, x equals 1 minus t, if I just look at that, x as a function of t. So notice here I'm looking at the t-axis and the x-axis. So x as a function of t. And I draw that graph. So if I draw that graph, 1 minus t, let's see, that has a, I was going to say y-intercept of 1, but that is the x-axis here. But it would go through when t equals 0, x equals 1. When t equals 1, x equals 0. And so we get something that looks like this. Okay? So what that means, we've got to pay close attention to what variables we're talking about. That means as t increases, so as we go to the right on this graph, as t increases, x is the vertical axis here, so that is getting smaller. So this is telling me as t increases, x gets smaller. In fact, let me write that relationship. As t increases, x gets smaller. And you could even say it's getting smaller steadily. It's not like getting smaller really fast or really slowly. It's just kind of getting slower, lower, smaller, kind of evenly, uniformly. Okay, now I'm going to look at this relationship here. This is y as a function of t. So once again, notice carefully the way that I have these labeled. And I probably could have made them stand out even better because these are important. So make sure you highlight those. Maybe we want to even put those in red or something. This is really important. Okay, so if I'm just looking at how y depends on t, I'm just drawing this function y equals t squared. And y equals t squared would be, go through 1, 1, 2, 4. It's just a parabola. Like so. Whoops, 2, 4. So this is telling me the dependence of y on t. So let's talk about what's going on there. So as t increases, so t is increasing. As t increases, what happens to y? Well, as we move to the right, y gets smaller all the way down to 0, and then it gets bigger. So as t increases, y gets smaller down to 0 and then bigger. Okay, so here's how we're going to use this. this is telling me, we're trying to figure out how, this is how x depends on t. This is how y depends on t. They both depend on t. You know, both the ice cream and the sunscreen depended on temperature. But then how does that mean these two are related? So that's what we're wanting to look at here. When we put this together, what is it telling us about how x is related to y? And so here's the way we're going to think about it. As t increases, x gets smaller. So on this graph, what that means is as t increases, x gets smaller. X getting smaller means we're moving to the left. Okay, so what this tells me on my graph below is on the graph below, x gets smaller means I'm moving leftward. So I don't know what my graph looks like here, but I know that it's going to the left. I don't know anything about the vertical yet, but horizontally, I know that we're moving to the left the entire time. X is getting smaller as t increases. All right, now what does this tell me? As t increases, y gets smaller down to 0, and then it gets bigger. So as t increases, okay, so like when t is -2, y is all the way up at 4. Okay, so we're way up high, and as t increases, y gets smaller down to 0, so that means we're going downward, but only to 0. And then y gets bigger. So, and I'm not trying to put the two together yet. I'm reading what they're telling me separately. This is telling me on the graph below that y starts high. As t increases, y goes down to 0 and then back up. So if I'm just keeping track of vertical motion, I know I'm going to go down and then up. Okay? Now, putting these two together is kind of an interesting technique. And you're going to see that we're going to have even a better way to do this in a minute. But this technique is one you should practice, because as you go on higher in math, being able to look at what these graphs individually tell you about this graph is going to be very helpful. All right, so what's happening? We're saying that we have a graph that's moving to the left. So my left hand, picture me drawing this, my left hand is just going to pull to the left the whole time. I'm also going to put my right hand on the pen, and my right hand is knowing to go down and up. So all my right hand knows is I'm going to go down and up. And while I'm going down and up, my left hand is going to pull me to the left. So down and up and to the left, and I'm going to get something like this. Okay, it's kind of hard to picture this when you can't see what my hands are doing. But the point being is this one is telling me about the horizontal motion, and this one is telling me about the vertical motion. And so we put those together. Now, if we want to be even a little more specific, one of the things that we sometimes do is look at a specific point. So if I were to look at, say, t equals 0, at t equals 0 on this graph, x is 1. If t equals 0, remember this is my t. If t equals 0 on this graph, my output is 0. That's my y. And so looking at those purple dots, it says when t equals 0, x is 1, y is 0. So we would be at the point 1, 0 when t equals 0. Now, we already have these dots on here from this, but typically we're not going to do both. We would do this or this. Okay. All right, so what do we do from t equals 0? When we leave t equals 0, we already said that horizontally we're going to be moving to the left. So leaving this point, we are going to be moving to the left. And what are we doing vertically? Well, vertically, we know that we go down and then up, but let's look at what happens from t equals 0. From t equals 0, as t increases, y is getting bigger. So from t equals 0, we're just going up. And so this is telling us that from t equals 0, we're going to go to the left and up. Well, I could draw it like that. To the left and up. All right? So put that together with what we've kind of seen so far, is we know we're moving to the left and up, and we happen to know that we have those points as well. Okay, so we're moving in this direction from t equals 0. If we look at what happened before t equals 0, it's the same thing. Y starts up high and gets smaller. We're moving left the whole time, and so we end up getting something like so. Those arrows that I drew on the graph, you know, we're used to putting arrows up here. These arrows mean something different. These are showing the dependence of x and y on t. And so one of the places where we really use parametric equations a lot, and the reason why I use time for a parameter a lot, is because we use this to discuss motion on a curve. If I just draw a parabola, we can kind of think of that as a path or a roadway that we're going to take. But if we put dependence on time, then it suggests we have a particle moving along here, or somebody driving their car along here. At t equals 0, we're here, and then t equals 1, and then t equals 2. So that time information, if we want to carry it along with us, that tells us a lot more than just the path does by itself. So that's one of the things we're really going to use parametric equations for, is to find out that not only is x related to y, but they are also dependent on some other parameter. Okay? So that's what this says. Always show the direction of increasing t. That means you're going to have these little arrows. All right, the third method that we can use, what do we got so far? Plotting points, that's our last resort. Looking at x and y separately as a function of t, and then combining that information. The third method, when it works, is the most efficient. Right? So the third method is what we call eliminate the parameter. Oops. And the parameter here, in this case, is t. And so we go up to our original equation and we're saying, okay, we want to combine these together to get an equation that has only x and y in it and no t. That's what eliminate the parameter means. And so the way we can do this, and each of these is a little different. You won't always do the same thing. But oftentimes what you can do is take one of those two equations and solve for t. So t here would be 1 minus x. And then you substitute that value for t, and we get y equals t, which is 1 minus x squared. Now you might be more familiar with it seeing it this way. Those are equivalent because inside that parentheses, those are just opposite. So when we square them, they're the same, right? Now this, in this form, we should recognize this. This is just a parabola shifted 1 unit to the right. So parabola shifted 1 unit to the right would just, you know, if I said, okay, what's the graph of this? All we'd have to do is go up, looks like this. We wouldn't have had to do any of that work we did previously. We would have been able to jump right to that final graph. So that's why this is the most efficient way if you can do it, because it brings us back in the world of y and x, and that's where we have a lot of experience. Now the only problem with doing this, well, one is that you can't always do it. That's one. But the other is that once you eliminate the parameter, you lose good information. So if I asked you to graph this here, you would graph your parabola, but you've now lost any dependence on t. So if we're talking about wanting to understand the motion of something moving along that curve, we've just lost all that information. All we see is the road, not the travel. So the caution here is that we lose information. And not only do we lose information on t, but we're going to find that we sometimes lose information about domain, which we'll get to in just a second. Okay? All right, so kind of probably too squished over here. I have this, what if I change the problem just a little bit here? Actually looks like a lot, but you'll see it's not really. If I made this the problem instead, and I eliminated the parameter, then what I could do is I could say, I don't even have to solve all the way for t. I get t squared equals 1 minus x from here. And then y equals t to the fourth, which is t squared squared. So y is going to be 1 minus x squared, which is x minus 1 squared. Okay, now this is an important point that I probably shouldn't have shoved down here in the corner, so tune in here with me. This is a different set of parametric equations than this. When I eliminate the parameter, though, they both are exactly the same equation, which means their graph would be the same. But the dependence on t is different, and here's the part that I was talking about. We're going to talk about domain information. All right, I decided to give us a little more room here. So this was what we did with the original pair of parametric equations. And what I said was that here, if I eliminate the parameter, I get this same equation in x and y. And so if we're just looking at a graph in x and y, both of these would be a parabola with the vertex at 1, 0. So parabola shifted 1 unit to the right. But when we eliminate parameter, we lose some useful information. Okay, so it's going to turn out that even though these equations are the same, their graph is not going to look the same here. And here's why. Let's take a look at what this tells me here. Here, as x is a function of t, then it looks like x equals 1 minus t squared. That is a parabola that opens downward, goes through 1 and 1, opens down. This is x as a function of t. And so this is telling me that as t increases, what does x do? X goes from negative infinity, it increases to 1. That's the highest point where it is right there, is 1. Remember, x is the vertical axis here. And then it decreases. So now translate into what that means over here. As t increases, x goes from negative infinity, so just looking at horizontal motion only, x is way out here, and it's going to increase, so we're going to move to the right until we get to x equals 1, and then we're going to move to the left. That's just the horizontal motion. Now, the vertical motion, y equals t to the fourth, is similar to y equals t squared on the last page there. And so y is going to go down and up as before. But this is changing something. Notice this is saying the most x is ever going to be is 1. And what that means is we have no graph over here, because x is always greater than or equal to, whoops, I said that wrong. X is less than or equal to 1. So there is no graph over here. And so what this graph is actually going to look like is y goes down and up, like we said, but x goes right and then left. And so our graph is going to come in like this. It's going to come in, x is increasing, and then it's going to turn right back around and go up the same path. I just didn't draw it on top of there so we could see it both. That describes a much different motion. Here we're talking about an object traveling along this path like this, right to left. Here we're talking about an object coming in, turning around, and going back. These equations are the same, but because the parameterization was different, it led to different motion. Okay, we'll see some more of that as we go on. Okay, here's an example as well. So suppose I asked you to sketch this, and rather than do each of the cases, plot the points, look at x of t, y of t, eliminate the parameter, I'm going to go ahead and jump straight to eliminate the parameter if I can do that. That's typically what we'll do. Now, you could solve this for t and then substitute t into there. But as I told you, sometimes there's different ways of doing these. You don't always have to solve for t. So in this one, for instance, kind of similar to the last one, e to the 2t is e to the t squared. That's the same thing as e to the 2t, but e to the t is x, so this is y equals x squared. So my first thought at what the graph looks like, and I'm going to erase, so you might not want to draw this yet, but this is my first thought of what this graph would look like. It's a parabola. But then we want to look at what kind of lost information is there, and what about the direction of increasing t? Okay, in terms of the lost information, think about x equals e to the t. Now you may not need to draw it. You may know what I'm getting at just by talking about it. But if I were to draw x equals e to the t, so make sure you label your axes here. X equals e to the t looks like this. And so that would mean that as t increases, x increases, and this should be going up even steeper. X increases exponentially. X gets big fast. Okay? So as t increases, x is increasing. X increase means and I'm even going to put in the word fast here. It gets big fast. So that means on this graph, as t increases, we're moving to the right. X gets big means moving to the right. But on this graph, you can see that x is always greater than 0. E to the t does not go below the x-axis. So note, x is always greater than 0, not even equal to 0, greater than 0. And so that means that over here, x can't be 0. So x is going to be, as t goes to negative infinity, x gets close to 0. But it never equals 0, so something like this. And then it's going to move to the right fast. Now, if you need to also draw y as a function of t to give you more information, you can. Typically what we do is we eliminate the parameter, and then in order to think about whether or not there is lost information, we can just think about these functions or maybe graph one of them. Okay? But what my final graph is going to look like is going to look like this. And be very specific about what's going on here. Make it very clear. It does not contain that point. That point corresponds to x equals 0, and x is never 0. We don't ever cross this x equals 0 line. Okay? The direction of increasing t, as t increases, x increases, so we're always moving to the right. In terms of that idea that x gets bigger faster, gets big fast, we could put in a couple values for t. I told you sometimes we want to carry that information along. So for instance, if t equals 0, I would be at the point 1, 1. If I put in t equals 2, I'd be at e squared. Now, e is almost 3, so e squared almost 9. Putting in t equals 2, I get e to the 4th, so almost 3 to the 4th, almost 81. So by t equals 1, we're way off the chart. So we got this thing going along from, negative time, negative 100, negative 10, negative 2, negative 4, 0. I guess I could have put in 1. 1 would be e squared. So even that, this corresponded to t equals 0. T equals 1. So we're moving slow, 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 slow. T equals 1 is already up here, and then t equals 2 is the next floor up. Okay, so I hope that shows you a little bit about when you eliminate the parameter, you do have to go back and look and see at anything else that was implied here that you left behind. And in order to do that, you could look at the graph of x of t of y or y of t. Look at things like the domain or range of each of these individual functions. Okay. All right, one of the other helpful ways that we use parametric equations is to, sometimes we are able to take something that's not a function and express it in terms of two equations that are, right? So for this one, even though we do have a way to eliminate the parameter and get right to it, before we do that, I want to consider that second approach just to give you an idea of how that approach works. Right? So let's look at x of t and y of t separately. And if I were you, I would make sure you highlight. They're there, but they're a little hard to see. And then this one is x and y. Okay, so you can see why it's super important to label those axes. We've got a lot of different things going on. All right, x equals cosine t. Cosine of t starts at 0, 1. And I guess I don't have the great scale here. What was I thinking? Let me just erase this. Let me erase this scale. This is not good for trig necessarily. Okay, so if this is, say, oops. We'll make this pi over 2 and pi and so on. So cosine we've got going like this. And sine, we go from 0. So 0 to 1 to 0 to negative 1, so on. Okay. All right, so I want you to try to picture this, to use your imagination here a little bit. Here's what's going on. How do we read this? Let's just start at a specific point so we have something to look at. Let's look at t equals 0. So when t equals 0, that corresponds to that point there. T equals 0 corresponds to that point there. So when t equals 0, x is 1 and y is 0. So we would be at this point 1, 0 when t equals 0. Just so I have some place to focus my attention. All right, so then what happens? What happens on this next part of the graph here, say, is x goes from 1 to negative 1. So that means as t increases horizontally, we're going from 1 to negative 1. This is only telling me about the horizontal movement. And then after we go from 1 to negative 1, then we go back to 1. So then we go back to 1, and it just keeps bouncing back and forth. So I have no idea about the vertical motion right now, but I know that my curve, my path, my object is going to move left to right, left to right. Now keep watching my left to right. I don't know what vertically it's going to do. You know, maybe it just goes like this. But horizontally, I know it's going left to right that whole time. All right, now separately, let me look at what's going on vertically. So I learned about vertical from the y. So at t0, we're here at y equals 0. And then as t increases, the first thing that y does is it gets bigger. It goes up to 1. So just vertically, not looking horizontally, we know that as t increases, we're going upward. So actually, if we put these two together, we're going leftward and upward from this point. Okay, then what? Right here, t goes upward. Y gets bigger, so the graph over here goes upward, and then y goes down to -1. So that means over here the graph goes downward, and then it keeps going back and forth. And so you start trying to imagine this. Hold on to the pen with both hands. My left hand just wants to go back and forth, left and right. My right hand just wants to go up and down. I put both hands on the pen. I need to be going left and right and up and down, maybe something like this. Now this is just very rough. There's lots of ways we could be going left and right and up and down. Okay, but that's the idea. What I want you to get is the idea of how you can take each of these separately and try to put them together. It's challenging, and we'll look at some more examples, but it's going to be a useful skill to have. This animation, they don't work well to show them on the videos, but if you go to the 5B page and you click on that link there, it will do exactly what I was showing you. It'll show you how this point wants to go left and right, this one wants to go up and down, and when we put them together, where is this point actually going? Okay, so take a look at that, and if you want me to explain that animation in class, I'm happy to do that. Okay, to actually eliminate the parameter. So what I really would do is first try to eliminate the parameter. I was just trying to teach you something here. To eliminate the parameter on this kind of problem, there's a nice trick you can use. You could solve for t. You'd have to incorporate cosine inverse and then put that in there. So you could do that. But there's a technique when you have cosines and sines that is really useful. You take your equation and you see that the cosine is isolated over here. So I'm going to square both sides there. So I have a cosine squared on the right. And I'm going to square both sides here. So I have a sine squared on the right. And so that gives us this, the left side is x squared plus y squared. And the right side is cosine squared t plus sine squared t. So at first glance, it doesn't look like I eliminated t. But Pythagorean identity, cosine squared plus sine squared is 1, and so I get y squared, x squared plus y squared equals 1. So I get the unit circle. And you could see whether or not where's 1 here? You could see whether or not you believe that what we said was going to happen is what's happening. This is going left and right, up and down, left and right, up and down, and we're getting something like this. All right, so with the cosines and sines, that's often a technique for eliminating the parameter. What direction are we going? Well, we already said that at t equals 0, we're starting here. Okay, and from t equals 0, this tells me that x is getting smaller, so I'm going to the left, so we know we're going to start out by going to the left, but that could be either this way or this way. Those are both to the left. This one says as t equals 0, y is going to start by getting bigger. So that means we're going to start by going up. So if we're going to go to the left and up, that is telling our direction of increasing t, left and up goes this way. So we are going around this path in a counterclockwise motion. Now that idea of how we find the direction of increasing t sometimes takes people a minute to get. So I'm going to do another example like it. But keep in mind, from what I knew that t equals 0 was here. My question is just, am I going this way, which would be up and left, or am I going this way, which would be down and left? Either way, from this point, I'm going left. So the question is up or down. If you want to know about up or down, then you want to know what y is doing. Here's another example that addresses not only the direction of increasing t, but also the idea of using sine and cosine to eliminate parameter. So in this case, I have these coefficients. So just squaring these is not going to help. I would get 4 sine squared and 9 cosine squared, which does not give me 1. But if I were to isolate the sine and isolate the cosine, and now square both sides, then on the right hand side, what do you have? Same thing, right? Sine squared plus cosine squared, that's 1. That's how we eliminate the t with sines and cosines. 1 possible. On the left, I'm going to get x squared over 4 plus y squared over 9. So we should recognize that. That's an ellipse. We go 2 units in each of the x direction and 3 units in each of the y direction. And so we get this an ellipse. Now, what about the direction of increasing t? Okay, so think with me here. Typically what I do when I want to find the direction of increasing t is I look at what happens, say, at a given point. When t equals 0, sine of 0 is 0, cosine of 0 is 1. So when t equals 0, I would be at the point 0, 3. So right here, this is t equals 0. And so basically, we need to know which way are we going, around this way or around this way. You know, the path is either this way or it's this way. So how do we decide? Do we have to go ahead and graph x of t and y of t and all of that? Well, here's what I'm looking at. My 2 choices are left and down or right and down. From this point, you're going left and down or right and down, right? So either way, you're going down. The question really that we're asking here is, from this point, are we going left or right? That's all I need to know. And so what do I want to look at? I want to look at what x is doing. So I don't really need to look at x of t and y of t both. I only really need x of t, left or right from that point. So what does that look like? X is 2 sine of t. So 2 sine of t goes 0, high point, 0, low point, and this is not to scale. Okay, so just take off that scale on the x-axis. The point being sine goes 0 high, 0 low, 0. So what does that mean? It means that x goes from 0 to 2. As t increases from 0, x increases from 0 to 2. It means we're going to the right. X increases implies we're going to the right. And so there's our direction of increasing t. Okay, so we don't even need to do that part. Okay, so you might need to look at this. This is a question that some people get right away and others takes them a while to see. So come back and look at this example, these last 2 examples. Sometimes you're given some restriction on t. All that means is that we're just looking at a specific portion of the curve. So this is the exact same graph that we just drew. Okay, so it would, initially I would think I should draw that whole thing right here. But I only want the part where t goes from pi over 2 to pi. So when t equals pi over 2, here, sine of pi over 2 is 1, cosine is 0. So that's going to give me a 2, 0. And when I put in pi, sine of pi is 0, cosine is negative 1. So 0, negative 3. So it's actually going to be just 2, 0 to 0, negative 3, just this portion right here. So just here. Still draw the direction of increasing t. And maybe label t equals pi over 2, t equals pi. So that's how we look at just a portion of a curve. Right? There is another nice animation on the 5B page where it looks at what x and y are doing separately, and then you see what they're doing together. All right, on this problem, and there are problems, if you're in calculus, it's in section 10.1, in the pre-calculus, depending on what book we're using at the time, or I'll give you a worksheet. But the idea of this is the second way that we learned how to graph. Okay, there was plotting points, that was the first way. There was eliminating the parameter, that's usually the most effective way. But the other way is to graph x of t and y of t separately and put those two together to see which x and y. Let me write y of x. It doesn't mean y has to be a function of x there, but I'm just looking at, x as a function of t, y as a function of t. How does that give me x in terms of y? So this is a matching problem. So we're looking at which pairs of these, so here is a pair, which one of these graphs does it correspond to? Here is a pair, which one does it correspond to? So this is a good thing for you to play around with. This checks whether or not you actually know how to read those graphs and use them. And it's going to be especially important when we go higher and we're in 3 dimensions. Okay? So I'm going to put the answer up here in just a minute, but I would encourage you to stop the video and see if you can answer it. Okay. I'll share with you some of my thought processes. There's lots of ways to think about these to get the job done. Let me just start with, well, here, you can either start with any pair or you can start one of these and think backwards, either way. And I can share with you some of the logic on both of them. But in this particular case, I noticed that these, x only goes from negative 2 to 2, y only goes from negative 1 to 1. Here, x goes from negative 2 to 2, y goes from negative 1 to 1. But these are different. Here, x goes from 0 to 4. Y goes from, it looks like, negative 3 to 1. Here, x goes from negative 1 to infinity. Y goes from 0 to infinity. Again, I'm just talking out loud of how I might approach this. But what I'm saying is this graph here is kind of unique in that it is x goes from negative 1 to infinity, it appears. So x is greater than or equal to negative 1, and y is greater than or equal to 0. So corresponding to this, over here, we would have to have a graph where x is greater than or equal to negative 1. So for instance here, this is x in terms of t. X can only go down to negative 1. So x can only go this low. Remember, x is the vertical. X can only go to negative 1. X can only go to negative 1. X can only go to negative 1. Okay, so it looks like, unless I've misread it, it looks like this is the only case where x goes down to -1 only. Okay? Now, to see whether or not we believe what's going on there, to go with that, we'd have to have the situation where y is greater than or equal to 0. Y is this graph. Greater than or equal to 0 would mean it'd have to be above here. So y greater than or equal to 0 would mean the graph is only above there. And the only one where the y graph stays above there is here. And so these two together, the x is greater than -1, the y is greater than 0. Now let's think about it more completely, right? As x increases, or let's look at the y. As t increases, y starts at 0 and gets forever big. As t increases, y just gets big. We don't have something that goes up and down. This is just getting bigger. Okay? X, as t increases, x gets smaller, down to -1, and then bigger. X gets smaller, down to -1, and bigger. So these two correspond to that one. Okay, so just, I probably approach these differently every time I do them. So I'm just sharing with you some of the different ways you can go about thinking about them. So I'm saying this one, these go with this one. Okay, now let me do one where I think in this direction instead of that direction. So, and I'm just doing this randomly. Let me take a look here at these. So what do I read from there? As t increases, x goes from 2 to -2 back to 2. So that means we have some sort of 2 to -2 back to 2, horizontal motion. 2 to -2 and back. So it can't be this one. 2 to -2 and back. So it could be this one. 2 to -2 and back. So it could be this one. So far, it could be either one of those. Okay, in the meantime, y goes from 0 to 1 to 0 to -1 to 0 to 1 to 0 to -1. Okay, so y is going 0, 1, 0, -1, 0, 1, 0, -1 like this. Same here. So from -1 to 1. So it looks like it still could be either one of those. Right? Now if I start thinking a little more deeply about it, this one is going left and right a lot more than it looks like it's going up and down, if that makes any sense. So this is more likely to be here. X and Y are changing a lot. That means we're going left and right a lot. In addition, this is one cycle. This is one period, and it looks like around 6. Okay, this is probably cosine, and the period's probably 2 pi, but we don't know that. But it looks like one complete cycle where this is making 2 complete cycles. 1, 2. So that means for every one left and right, there's going to be up, down, up, down. So as we go left and right, we're going to go up, down, down. So you can kind of look at the period that way. So this one is going to end up going here. And similarly, that one goes there. Now to see if I believe our final answer, because sometimes I give matching problems where there's one that doesn't have a match. So it would be easiest for us to go, oh, these two go together, because they're the ones that are left. But if the instructions say one does not have a match, then, we don't know that for sure. So let's see if I could figure out what's going on here without just jumping to that conclusion. So when t is 0, I'd be at x equals 0, y equals 1. So when t equals 0, I'd be at the point 0, 1. And from there, what happens? X is increasing, which means over here that we're moving to the right. Y is decreasing, which means over here we're moving down. So we're moving to the right and down, and so that looks pretty believable that that does in fact go there. Okay, these we might want to talk a little bit more in class because there are animations that go with it. And as I said, the animations often don't show up well on this video. But what I've got for you, two facts. One is parameterizations are not unique. What I mean by that is if I took this pair and I eliminated the parameter, so I put in x there, I would get y equals x squared. Here, I don't actually need to solve for t, and I just have 1 minus t. So y equals x squared. So these both represent the same graph, although we did see that we have to watch for domain issues to make sure that, one of them isn't only a part of the graph. In this case, they both do generate the same graph. So there's many different ways to parameterize the same graph. Now, what's going to be different about these is their dependence on t is different. So for instance, if I put in t equals, say, -1, this pair over here, in fact, this pair over here, if t equals -1, is going to give me -1, 1. And this pair, if t equals -1, this pair here, -1 is going to be 2, 4. So that's what is shown on this picture. This is the purple parameterization, means I'm here at that time. The red parameterization means I'm here at the time. And so what's happening is, yes, it's the same path, but these are each describing an object with different motion. In fact, look at this for a second. If we looked at x as a function of t here, x equals t. So that would mean as t increases, x increases, which means on this graph, as t increases, x increases, that would mean we're moving to the right. So we have this object here that as t increases, it's traveling on the path like so. Okay? But look at the other one. Look at the red one. Whoops, the red one. So there we have x equals 1 minus t, and 1 minus t looks like this. When t equals 0, you're at 1, and then after that, I should label this, x is getting smaller. So x is getting smaller. So from this point, as t increases, x is getting smaller. That means we're traveling this way. So this object is traveling along this way. This one's traveling along this way. So same path, but different motion being described. Okay, but parameterizations are not unique. So if I said, give me a parameterization for this curve, you might do it this way. The answer book might do it this way. You're both right. Not unique. Okay, one other idea is to keep in mind that parameterizations are telling me about motion along a path. So it's possible that I have these two paths. They have different parameterizations. We have a parameterization that tells me about movement along this path here and movement along this path here. So two different sets of parametric equations, two different paths this time. Not two that give me the same path, two that give me two different paths. And in this one, I didn't write the parameterization down, but you've got an object moving this way and you've got an object moving this way. So think of two cars approaching an intersection. Are they going to collide or aren't they? Well, the paths definitely intersect. Okay? The paths cross for sure, but are the cars going to collide? Are they going to be here at the same time? And so this is on the 5B page in animation, but you'll see these things actually moving, and you'll see that yes, in fact, they were here at the same time. And then they kept going. So this one is moving like this one's moving like that. They were there at the same time, so we would call that a collision. And then they went on their way. Okay? It's possible, though, that we have two intersecting paths with objects moving along them that they don't collide. You know, think of two cars going through an intersection at different times. So this guy is moving along, this one's moving along. The red guy gets to the intersection first and keeps going. And then a little later, the purple one gets to the intersection, but the red one is long gone. So this would be a case where the paths cross, but no collision. Just something to point out. It's something that's going to come up later when you're given parametric equations, and oftentimes you're asked, are they the same path? Yes, these two are the same path. Okay, are they different paths? Yes, these are different paths. Is there a collision or is there not a collision? So the way you can tell if there's a collision is that both objects have to be there at the same time, same point at same time. Here, they both go through that point, but at different times. Okay, so a collision would be if they're at the same point for the same value of t. All right, so that should give you some insight into parametric equations. When you get to 5C, we do all this in 3 dimensions, so get a good handle on it now. All right,